So question 47 from the homework, we're given the information that we have to heat 500 grams of ethanol. We have to heat that from 25 degrees Celsius all the way up to 125 degrees Celsius. And they also tell us in that problem that the boiling point of ethanol is 78.3 degrees Celsius. So we have to do three separate calculations here. We have to go from basically ethanol, we have to heat the ethanol. So we have to go from 25 degrees to the boiling point, which is 78.3 degrees. And then we have to vaporize the ethanol. So first was to heat the liquid. Then we have to vaporize. So vaporize, that's right, isothermal, that stays at one temperature. That's going to be at 78 degrees. And then we have to heat it again from 78.3 degrees all the way up to 125 degrees, except for now we are heating the gas. So for that, we need some information, right? We need the heat of vaporization. They tell us the heat of vaporization is 39.3 kilojoules per mole. We also need the heat capacity of the liquid, and we need the heat capacity of the gas. So they give us in the question that the heat capacity of the liquid is 113 joules mole degrees Celsius, and of the gas, it is 420 joules mole degrees Celsius. So quite a bit of information that they give us there, right? The one nice thing about this problem is that all of these are per mole. Sometimes they'll put the first and the third one as energy per gram, because usually Q equals MC delta T, right? We're usually doing that per gram, not per mole. But all three of these are in mole. The one downside is that the middle one is in kilojoules. So we will have to do a conversion of energy at some point from joules into kilojoules. So our first calculation, Q equals moles, right? C delta T for the liquid. So for our liquid, actually calculation before this would be to find moles, right? I know I've got 500 grams of ethanol, and ethanol is, I think, 46 grams per 1 mole. So I've got like 10.87 moles of ethanol. So 10.87 moles. The heat capacity is 113 joules mole degrees Celsius. My delta T, I'm going from 75, from 25 to 78.3. So my delta T is 53.3 degrees Celsius. The second one we'll skip for right now, and we'll go to the third one as well, because that's also going to be Q equals number of moles times the specific heat of the gas times temperature. So Q 10.87 moles. The specific heat of the gas is 420 joules mole degrees Celsius. And our delta T of that last transition, right, we're going from 78 to 125. That delta T is 46.7. The middle one, right, Q equals moles times my heat of vaporization. So delta H, the energy required to boil, right, take that liquid and turn it into a gas at 78.3 degrees. So Q equals 10.87 moles. The heat of vaporization, 39.3 kilojoules per mole. All right, multiply all of those, and let's just take a quick look. Moles cancel, degrees Celsius will cancel, moles cancel here, moles cancel, degrees Celsius. That's good. So everything that's left is just joules or kilojoules. So for the first one, I get like 65,000, 468 joules. The next one, I get like 427 kilojoules. And the last one, get huge, 213,204 joules. So the last step, right, here's the energy from step one, energy from step two, energy from step three. The last step, I want to add all of these together after I convert the first and the second one into kilojoules. So essentially, I've got 65 kilojoules from step one plus 427 from step two plus 213 kilojoules from step three. Add all those together. Overall, we're going to get like 705 kilojoules of energy required to heat the ethanol from 25 degrees to the boiling point, boil the ethanol, turn it from a liquid into a gas, and then heat that gas from the boiling point up to 125 degrees Celsius. So 3 steps, 2 different calculations, right? We're heating a liquid, we're heating a gas, and then we went through that phase change for that substance. So hopefully 705 kilojoules, I forget who asked the question, puts you in the right range.